Hi everyone. So our project is particle swarm optimization. So we'll be going through three main parts: introduction, analysis, and conclusion. And these are the subparts which we'll be covering over this PPT. So for the first part, introduction, we'll be understanding what actually PSO is and what is the concept behind this algorithm. So basically, PSO is a optimization algorithm which was inspired by the behavior of a swarm of fishes or birds. So it is a real life scenario in which a flock of birds generally search for food in a forest or woodland. So these birds are unaware of the exact location of this food, but they have some sort of an idea of the distance and the direction of the food from them. So basically, each bird individually makes an effort to locate the the position of this food, but is also influenced by the decision or the direction in which the flock of birds move. So the same concept is applied to PSO, in which the goal of this algorithm is to find the best solution in a search space. So it does this by using a population of solutions, generally particles, which move across this search space and in according to a mathematical formula, which is again with respect to the particle's position and velocity. So at each iteration, PSO enhances its solution with respect to a specific metric, which is again based on the local best known position of that individual particle, but also the position of the swarm in general. So it is anticipated that the swarm will help this algorithm find the most effective answer. So generally, PSO is used to find the maximum or minimum of a function, which is defined on a multi-dimensional vector space. So the problem statement that we'll be approaching in this project is we'll be exploring the different objective functions that have real world applications, as well as checking the performance of PSO on these problems and basically drawing a comparison between these different objective functions. So for the analysis part, first we'll go through the mathematical formula. So as discussed, those particles move in a search space according to the position and velocity, and the velocity is calculated as follows. And these are the different parameters which I'll be going through. So first part, as you can see here, it's generally used for diversification, which is searching new solutions and finding the region which has the best solution. So the W over here is for the inertia weight. So basically, if W equals to 1, the particle continues moving in the same direction. But if it is in the range of 0 to 1, the particle basically changes its direction. So it basically changes the direction of the particle. The next two parts are used for exploring the previous solutions and finding the best solution for a given region. So for the personal influence is used to improve the individual particle's position. So for example, the particle has moved to a new position, but the previous position was the best position, or basically it was better than the current position. So this particular equation will make the particle return to the previous or the best position. And the last over here is social influence, which means that the particle will always try to follow the best direction of its neighbors. So if there's a particle and its neighbor are moving to a new best direction, the particle will also follow the direction of the swarm. So the objective functions will be explained by Raghav.
Hi, everyone. In our project, we have tried to tackle 4 different objective functions. One of them is Golinsky speed reducer. The other one is Ackley function, Rosenbrook's valley, and the last one is egg crate function. If I go through Golinsky speed reducer, this problem represents the design of a simple gearbox, such as might be used in a light airplane between the engine and a propeller, which allows to rotate at its most efficient speed. In this problem, the objective is to minimize the speed reducer weight while satisfying the number of constraints. And the number of constraints are 11, which are imposed by the gear and shaft design practices. So it is basically an engineering problem which we are trying to solve. And there are 7 design variables that are available to the optimizer, and each has an upper bound and a lower bound imposed. So this means that we need to get the maximum weight, the most optimized weight, taking in consideration of all the other parameters that are available to us. So if I go on to the next function, which is the Ackley function, the Ackley function is a non-convex function which is widely used for testing optimization algorithms. In its 2-dimensional form, it is characterized by a nearly flat outer region and a large hole at the center. The function poses a risk for optimization algorithms, particularly in hill climbing algorithms, which in that basically there's a fear to be trapped in one of the many local minimas. As shown in the formula below, D is the dimension, and the recommended variables through reading after some references are A equal to 20, B equal to 0.2, and C equal to 2 pi. And for the next two objective functions will be discussed by my co-team member.
Hello, my name is Shalvi Desai, and I'm gonna explain the two of the objective functions that we have used for our particle swarm optimization problem. And first one of this is Rosenbrock's valley objective function, and it is also known as Rosenbrock's banana function because of its parabolic flat, like because of its parabolic shaped contours. As you can see, the function is defined as a minus x the whole square plus b into y minus x square the whole square. As per our results, the global minima is obtained at a comma a square. Here a and b have to be determined by us. We, in our scenario, we have set up a as a equals to 1 and b equals to 10. So our global minima should be around 1 comma 1. And usually these parameters are set so that a is equal to 1 and b is equal to 100. So its global minima is around 1 comma 1. Only in trivial cases where a equal to 0, the function is symmetric and minimum at the origin. Otherwise, it is a long, narrow, parabolic shaped flat valley-like structure. The second function that we have used is egg crate function. In this problem, there are two design variables with x1 and x2 with lower and upper limits of minus 2 pi and 2 pi. We have used particle swarm optimization to find the optimal solution for solving this problem. As per the results shown, that crate function has a known global minima at 0, 0 with an optimal functional value of 0. And hence, given coordinates x1 and x2, here xi is like x1 is equal to minus 5 and x2 is equal to 5 for the parameters or the variables x1 and x2.
Yeah. So hello everyone, I'm Sumit. So now that we know the basics of particle swarm optimization, and now that we know that we know the problems that we are tackling through this optimization technique, so it's time to look at the algorithm itself, so how it is done. So first we start with initializing the swarm. So how is the swarm created? So for the swarm, we need particles, and for the particles we define a particle class, and for each of the particle we have various other features. So like each particle has its cognition. Cognition is nothing but the its own intelligence, like how much it is affected by its own knowledge and facts. And then it has the social. Social is nothing but its dependency on the knowledge of the swarm, and it also has its own inertia. So inertia is self-explanatory. So it's like tendency to move in a particular direction. And each particle also has a bound, so it can't go beyond those bounds, and it has its own constraints which it has to satisfy. So initially, we initialize the position and velocities randomly depending upon the bounds, and then we initialize a swarm with number of particles, say 30 or 60. Then for each particle in the swarm, we compute its fitness values. So how is the fitness value computed? So for each of the particle, we calculate its value for the cost function, for the function that we are trying to optimize, and then we see if the error is lesser than its best error. If it's lesser than the best error, then we assign the new error as the best error. Next slide. Now, after calculating the cost for each of the particles, we now find the particle with the best position, that is a particle which is closest to the global optimum. So after doing that, for each particle, we update their velocity. So how is the velocity updated? So like Karthik discussed earlier, so we use the formula for updating the velocity, where the formula consists of an inertia part, the cognition part, and the social influence part. And where C1 is the cognition, C2 is the social influence, and R1, R2 are the random numbers. Yeah, next slide. So after updating the velocity, we also update the position of the particle. So once after calculating the velocity, we update its position, and after updating position, we also check if the constraints are satisfied by the particle. So if the constraints are not satisfied, then we don't move the particle, and we also check if it's going out of bound or not. If it's going out of bound, then we clip it according to the given bounds, and yeah, we do this for each of the particles in this form. So after doing all these steps, we check if the stopping criteria is met or not. In our case, we have used the maximum iteration as the stopping criteria. So once the number of iteration has reached the maximum iteration, then we return the best position and the corresponding error. So right now it's time to look at the runtime analysis of the algorithm. So for creation of the swarm with n number of particles having d dimensions, it takes O of n d time. And for fitness evaluation, which is done for each particle in the swarm, and for each particle, and for the sum we also find the best particle. So this can be done in O of n time, as we are iterating over each of the particle in the swarm. And after that, we update the position of the particles in this swarm and their velocities as well. So calculating the position and velocity across all the dimensions of the particle needs O of nd plus nd time, which is nothing but O of nd. And since here we can see the step 2 and 3 are repeated quite a few times until we reach the convergence or the stopping criteria is met. So in our case, our stopping criteria is the maximum number of iterations. So the runtime becomes O of in plus O of ind. And the total runtime is nothing but the addition of all this, where the first term is nothing but the time required to create this swarm, and then the other two terms are nothing but updation of the velocities positions and searching for the best particle. So the total runtime becomes O of nd plus in plus ind. And now the results will be discussed by Raghav.
Yes, so we did run our objective functions for 30 iterations each, and as we can see for Golinsky function, as we can see, we are talking about Ackley function, and the minimum of Ackley function is attained at 0, and after 30 iterations we can see that the best result that we are getting is like really close to 0. So these are some of the good results that we obtained after running Ackley function objective. And if I talk about Golinsky function, we did run it for 30 iterations, and the best solution that we got for the weight of the gear was around 2934. So after reading some books and references, it was mentioned that the optimal weight for a gear should be around 2985, and we thought that we could achieve a close result to the optimal solution, so we did pretty good on that.
Here is the result for the Rosenbrock Valley. The best position that we have obtained is 3.18 and 10, and the best solution that we have obtained, the functional value is minus 8.9. Now, as we discussed earlier, the global minima should have been at 1,1, since the value of A and B is 1,10. Since it's 3,10, there is more scope of improvement in our algorithm. And for accurate function, our best position is at minus 0.0010 and minus 0.0019, and our best and the functional value is 1.322. So I guess this is still closer to the global minima, because as you can see, the global minima is obtained at 0, it's almost like 0,0, and the best solution is 1.3, which is not that far from 0. So yes, these are the two implementations of our objective functions that we have used.
I'll discuss the pros and cons that we faced with PSO. So pros were like, it is very insensitive to scaling of design variables, but at the same time, it was very efficient in a global search as a global search algorithm. It was a simple implementation and could be easily parallelized for concurrent processing. And being an optimization algorithm, it was derivative free as well. So because of that, we had like very few algorithm parameters. And if we talk about the cons, tendency to a fast and premature conversion in mid optimum points was one of the cons that we faced as well. If I talk about the other point, there were like some slow convergences in refined search stage. So these were the two cons that we faced during the implementation of the whole project. And for the conclusion part, the most intriguing feature of PSO is its stable topology, which next slide, please. Yes. So if I talk about the conclusion, the most intriguing feature of PSO is its stable topology, which basically allows the particle to communicate with one another and then speed up learning to reach the global optimal. So as talked about in pros, this tells us that it was a simple algorithm to implement, and yet it is very effective. So this optimization algorithm's meta-heuristic nature provides us with a wealth of chances, because it's an optimization problem which is done by repeatedly attempting to enhance a potential solution. Also, moreover, the research being done on ensemble learning, I think, will take it to another level and make it applicable in a wide variety of real-world problems.